Okay, so talk me through this, please. Okay, good. So if I want to enter data, we always go stat. We want to go to the stat screen. So stat, edit, perfect. Okay, and then this is where we would, we put the data in. If there's stuff in there that we want to get rid of, you have your choice of either just writing over the top of it, or how could I just get rid of all the stuff in each column? Good, go to the top and hit clear enter, or clear down, I think does it also. Okay, so take a pick, but this is the right data. I've already got it in from last period. So this, remember, X is going L1, Y is going L2, right?
Yeah.
Once I get the data in there, now this is a little harder regression problem than the other ones that you guys probably, we worked mostly on yesterday. This is one where we don't just want the slope and y-intercept of the regression line. We actually want to know what's the value of y when X is 27. And so we got to do the regression, first of all, with one really important step. How do I get to the regression screen? Stat calc 4, right?
Do it.
Stat calc 4. And I don't get the fancy one. You guys get the fancy one. I get this one. But then on this screen right here, if I want to do something like this, if I actually want to build the linear model, in other words, graph the line, remember that on your screen where it says store regression equation, that's important.
Alpha.
What has to go right there?
Y1.
Y1.
Instead of first.
We got to put a Y1 there, right? So where do you get a Y1? There's two places. Where's one way is the shortcut. Okay, so everybody look at this. If you have a TI-84, you can go alpha F4 and it takes you to the little pop-up menus and you can get Y1 that way. Now you can always get it through the other really important menu, which is, how do I get out of there? I don't know. But if I go second calc, maybe, yeah, second calculate, it takes me to the graphing menu. So anytime I have something graphed, and hey, am I doing the right thing here? No, it's the wrong one. Never mind. It's not the one I want. If I want to put in a Y1, I'm sorry, the other menu we can use is the variables menu. So variables, Y variables, and this is like the TI-83 method. Variables, Y variables, function, Y1. Either way, my goal is just to get a Y1 there, right? Once I get the Y1 there, and on the TI-83, I just put it right after the linear regression statement. Then I hit enter. Good. And it does that. Okay, it does the regression stuff, makes the equation, but it also stores it as Y1. That's the good part, right? So I've got this equation in there. Now my goal is I've got the equation in there. I want to get the graph to where I can use it. So there's something really important going on with that. What do I have to do if I want to be able to use the line to evaluate the function at 27?
Go to graph?
Okay, I can't just go to graph probably. I mean, you might luck out, but
Tree?
no, I got to get the window set right. So I hit window, right? And the reason I'm doing this is because now it just so happens that yours are probably set up to do this correctly because we did these the last couple of periods. But normally they wouldn't be. Normally they would probably be set up to go from something like -10 to 10 or something like that. And this X value wouldn't be included. This is really important though. Remember that I need the X min and the X max to include that X value if I'm going to use it, right? And so I would have to adjust those accordingly. It's already set up to work this time, but if it weren't, I'd have to make one of them smaller or the other one bigger, but make sure that that's included, right? Once it's included, then I can just go, this is the other really important one. How do I make the calculator do work for me and pick the Y values, fit the Y values to my X values? Zoom 0, that's it. Okay, then we go zoom 0, right? So I go to the zoom menu, type in a 0, and it does it. It picks the X values that I established, which went from 0 to 35. 0 on the left, 35 on the right, and it just picks the right y values for me. I don't even know what they are. I don't have to know. Okay, so I got the graph up there. Now what? How do I use the graph to find the y value? Okay, if. Now this is you got to know two ways to do this though, because people get confused about this. Trace is going to work this time, but when I was looking out at a lot of you guys doing this a second ago, you had your plots turned on. And if the plot's turned on, the trace trick will not work, I believe. Okay, so you have to either go turn the plot off, or you can leave the plot on, but just use the old-fashioned, not the long cut, not the shortcut. So remember what that is. We can go second, calculations menu. That takes me to all the graphing calculations that we're able to do for a graph. A whole bunch of them. The one that we want is the first one, right? So I can hit second calc, value, and then it's going to ask me for the x value I'm inputting. So 27. Hit enter, and it spits out the y value. So 21.931, is that what we got?
Yes.
Okay?
Yeah.
Good, good. Okay, so then the other shortcut, though, you were telling me is a good one. I can just, if I only have one thing graph, I can just go trace and type the x value, trace 27. Okay? Right? Make sense? That's it. Okay, how many people, by show of hands, I kind of want, and I really, be honest with me here, how many people, tell me 1 to 5. 5 meaning, oh man, Mr. Ray, this is a piece of cake. I could do this with blindfolded, you know, backwards, behind my back, and everything. So 1 means I'm still struggling with this a little bit.
Struggling.
Okay? Okay? Okay, good. Well, then here's the solution. At your tables, I want you to, we're going to get one more practice.
Okay, now let's go.
Okay, you're doing this one.
Oh.
Do that. Attention right here, please. Okay, I want to, everybody, literally, I want eyes tracking me. I want to explain something to you. This is kind of an important thing. I want you to understand why we're doing this. Why are we going to deal with these things called piecewise functions? Okay, piecewise functions, what they do, we've always been used to in the past, been used to dealing with functions that only have one equation associated with them. So, and in math, a lot of times, just remember why we use math. A lot of times in math, we're not, probably very few people are going to be mathematicians per se, but a lot of people will use math to build predictive models. So if you are a forester, or something like that, and you're trying to make a prediction for a given forest, every forest is going to be different. For a given forest, you want to make some kind of a simple model that's going to make a prediction about how tall the trees are as a function of how old they are. So you might go out and collect some data. You take some tree rings, you do some samples, et cetera, and you would just get a bunch of data points, and then you would do probably regression. Now, it's probably not going to be linear regression, but later in the year, we'll continue this discussion, and we'll look at other kinds of regression, like quadratic regression and cubic regression and logarithmic regression and things like that. And this is far and away the most important thing you'll ever learn in this class, unless you're going to be a mathematician or an engineer or something. Because regression is the stuff that you probably will actually be able to use. Excel or a calculator, you'll be able to impress all your employers, and you'll rise up the corporate ladder quickly because you'll know how to take care of this data and produce some kind of model, and then you'll be able to answer the question, what if? What if a tree were this old? How tall would we expect it to be? And based on this regression model you build, it'll spit out a reliable number, okay, if you get good data, okay? And so that's really a lot of what math does. But even in that situation, face in the front, please. Thank you. Even in that situation, there's only going to be a single equation that represents the model. Okay? What happens in a more bizarre situation where the behavior changes? Like, let's take an example of skydiving. Okay, so if we look into skydiving just a bit.
Have you been skydiving?
I never have. Sounds like it'd be kind of fun. So if we do. So if we want to look at skydiving mathematically, and that's always our goal, is we want to see if we can look at this situation and tell a mathematical story about it. And a great way to do that, and I want to kind of train you to always think in terms of what a graph of a situation might look like. So for skydiving, our graph would probably be something like we're going to graph the height of the skydiver versus time on a graph. So we'd say as a function of time. And if we were to graph that, now you're going to tell me the story of what happens when you're skydiving. And as we do that, we'll sort of fill in the graph and see what the mathematical picture would look like. So now you got to use your imaginations here. We're starting from a big hot air balloon that's really high. If I jump off the hot air balloon, what's the well, first of all, when I'm on the hot air balloon, what am I doing?
Going up?
Okay, but we've gotten to the point where now it's even just, maybe it's just screaming, maybe. It's stationary, it's just hovering at 20,000 feet, I guess, I don't even, so it's pretty high, that's pretty high. Yeah. So anyway, we'll say it's at 15,000 feet, hovering, that's pretty high, I agree. But it's possible. So it's hovering there, I jump off the hot air balloon, and the hovering part might look like this. Off a balloon. Yeah, that's how that guy, you've seen the footage of that guy that jumped from the kind of the edge of space.
Well, it's not a hot air balloon.
His was not a hot air, it was a helium balloon.
I didn't see that. No.
Oh, it's amazing. Maybe if we have time at the end, we'll take a look.
We have time.
So here's the first phase. Listen, please. Wasting time. Here's the first phase of our story. It's pretty boring. That's when we're sitting in the hot air, or the guy's sitting in the hot air balloon. The height is staying the same as time passes, right? So that's pretty boring. But then things get exciting. He jumps off the hot air balloon, or the helium balloon, and what happens? Okay.
He's going down.
He's going down, but I need more description than that.
He had a jetpack on his back, so I was going up there.
What describe it? I need
He's going this way?
Okay, he's falling straight down. But what's happening to his speed?
Going faster?
Ah, okay, he's accelerating. He's picking up speed, right?
Yeah.
Okay, so the second part, I'm going to change colors. The second part might look something like this. From this point, it looks something like that, doesn't it?
Yeah.
Right? Do you see why? Look what's happening. As time passes, the rate at which he's losing his height is increasing. As time passes, he's losing height faster and faster. So the line gets steeper. Agreed?
Oh.
Right? Isn't that cool? Okay, but does he do that forever? Does he accelerate forever all the way to the ground?
Well,
No, he doesn't. In fact, he only accelerates for really a pretty short period of time. And then what happens?
Falls in the ground.
Dylan, he reaches what's called terminal velocity or terminal speed. Okay, now that's what happens, and for a skydiver, it's typically about 120 miles an hour. That's when the wind rushing past the skydiver, he's going so fast through the air that the drag with the air produces just as much force on him as the gravity pushes, his weight pushing him down, right? And so when you hit terminal speed, you don't get any faster. You just keep that really fast terminal speed all the way to the ground, unless hopefully your chute opens, and then that doesn't happen. But so from this point right here, all of a sudden now this doesn't curve anymore. It's just going to be a straight line when he's got that terminal speed. And that's as fast as he goes, right? Until he gets down to, that's a good spot right there, let's say. Until right about there, he pulls the ripcord. And then what happens? Okay, so the chute opens up, and then what happens to
It
his
goes
motion?
up a little.
Okay, now that's every class. They always say it, he actually doesn't go up. Now we oftentimes associate it with that because whenever you see footage of people skydiving, it's always from the perspective of what? Another skydiver. And so the other skydiver is actually, he's not going up. The other skydiver just continues to fall away from it, right? Does that make sense? So now instead, picture that you're watching this from a mountain instead. And so he's kind of fallen by you, out there in the distance by the mountain. When he pulls the ripcord and the chute opens up, does the guy in the mountain see him go up?
No.
No, he really just sees him kind of do this and just slow down, right? Okay. And so what would you call that period where the chute's pulling on him real hard to slow him down? What might you call that? Painful, possibly, yeah. There's a word. I'm trying to think if somebody can come
Does it
up
start
with.
with a V?
No?
Okay.
The one I'm thinking of starts with a D. What was it? Deceleration. There you
That
go.
was my third
Nice.
time.
Okay, so I look up here, please. Okay, so then he's gonna go through this phase where he decelerates. The chute catches the wind, so to speak, right? And it pushes up on him and slows him down, right? And so he's gonna go through a phase like this, where he slows down, and the line gets, its steepness decreases. He's still gonna be falling, but just very slowly. And then he actually hits a new terminal velocity, but this time the terminal velocity with the chute open is pretty slow. And so the last phase is going to be the peaceful phase where he just kind of gradually floats down to the ground, right? Now, if we divided this function up into pieces, if we wanted to try to come up with a single mathematical description of this, a single function, good luck. It's not going to work. You're not going to be able to find a single function, no matter how bizarre the equation, that does all that stuff. So instead, what you have to do is you have to just break this thing up into pieces. And so we've got this first piece of the function where he's in the balloon, and that's got its own equation. We've got the second piece of the function where he's accelerating, different equation. The third piece of the function where hits terminal velocity, he's falling at terminal velocity, that's a different equation still. He pulls the ripcord and he decelerates, well, there's a new equation for that interval. And then finally, when he just floats to the ground, there's even another equation. So we've got 1, 2, 3, 4, 5 different equations needed to describe that journey down to the ground, right? That's, that's strange, but that's a real, that we might want to do that. Okay, so how do we go about doing that mathematically? Well, we do it with what's called a piecewise function, right? If we need to represent more than one kind of behavior mathematically, that's how we do it. Piecewise function, because it comes in discrete different pieces with different equations. So here's an example of a piecewise function. And ignore, please, this line shouldn't be there. It shows up in this PowerPoint, but just pretend it's not there. There wouldn't be that horizontal line. So this is what a piecewise function looks like. Now notice that this f of x is equal to, we've got this kind of script bracket telling us there are multiple pieces to this equation. This one has 2. Ours had 5. This one only has 2. One piece is the equation 2x minus 1. So this function has the equation 2x minus 1 whenever x is less than or equal to 1. But when x is greater than 1, it switches over to this equation. You can literally think of the function being switched on or off depending on which x value you're interested in. Okay, so if I wanted to, now we're going to talk about graphing these things tomorrow, not today, but when we're graphing this, what that means is I'm going to be graphing a piece of the function with that shape, the shape that that line gives us, 2x minus 1, on this part of the xy plane, when x is less than or equal to 1. I'll be graphing a different line down here when x is greater than 1. But for today, all I really want to consider is, how do we evaluate these things? So if I wanted to do something like this, if I wanted to evaluate this function, and keep in mind what that means, we talked about that. That's just when we're plugging in numbers to get a number for the function. We're plugging in x values, plugging in numbers for x to find a number for the function. If I want to evaluate the function when x equals 0, what do? Well, the main thing to remember here is that when you are evaluating piecewise functions, only one piece of the function can ever be switched on at the same time. You can never have more than one piece working, because if you did, it wouldn't be a function. Then there would be pieces of the function that would overlap vertically, and that didn't happen, did it? Looking at our piecewise function, they did not overlap vertically. When one stopped, a different one started. When that one stopped, a different one started, but never was more than one piece working at the same time, right? So what about this then? What if I want to evaluate this at x equals 0? Oops, I gave it away. Do you see that that goes into the top equation? Because the top equation is the one that's switched on there. You can look at these piecewise functions as each row corresponds to a different piece, but each piece has 2 parts, 2 important parts. It has the equation part, and it has the domain part, which tells you where that equation is switched on, right? So when x is 0, the first thing I have to do is I have to look at the domains and see, okay, which is the one that switched on for that x value? Well, what's true? If I try to plug in a value of x equal to 0, is the top inequality going to be true or the bottom inequality? Is 0 less than 2 or greater than or equal to 2? It's less than 2, right? So that means that the top one is the equation that is switched on. And that's what I would plug x into, right? So I get back a value if I do that. If I plug 0 in for x, I'm plugging it into the top one, and I get 0 plus 2 equals 2. That's my answer. The value of the function when x is 0 is 2. What about when x equals 2? Where do I plug that in? Top or bottom? Which one switched on? Bottom, isn't it? Because when x equals 2, well, 2 is not less than 2, but 2 is greater than or equal to 2, isn't it? It's equal to 2. So that means the bottom is switched on there, so I'd plug the 2 into the bottom and get 5 for my answer, right? Okay, what about at 4? Bottom, good. Okay. And if I plug it into the bottom, 2 times 4 is 8 plus 1 is 9, right? So there you have it. So real quick, just try this. Try that one. You don't even need, just kind of on your own, I bet. Just look at this for a second. If I want to evaluate this piecewise function at x equals -2, and that's what that's saying, right? I'm plugging in -2 for x. First of all, which does it go into, top or bottom? Top, good, because -2 equals -2, right? So if I plug -2 into the top, let's see, 3 times -2 is -6 plus 9 is 3. That's my answer. Make sense? Okay, 205. Do the exit ticket. We can make it. We can make it.
I thought we were gonna walk the paper.
Oh, we don't have time.